Today we're going to talk about uniaxial stress and its relationship to Mohr's circle. What you see here is a prismatic bar that is loaded in a tensile axial stress. And in the figure down here, we're going to look at the stress distribution over the normal plane to the axis and the stress distribution over a plane inclined at an angle phi to that normal plane, which means that we're going to separate this prismatic bar and look at its equilibrium condition when we've separated it into two pieces. If we look at the cross-sectional area of that bar, we're going to call that capital A. The area over the inclined portion, that is the portion that is at an angle phi, will be given by A divided by the cosine of phi. And therefore, if we say there's a stress distribution S over this face, that stress distribution S will be given by the force distributed over that face divided by the area over that face. And therefore, if the stress over A, that is the normal face to the axial direction, is sigma x, which is P over A, the value for S per unit area is equal to sigma x cosine phi. Now, if we look at our prismatic bar, we can say that that equivalent S, which is in this direction, has two components: a normal component given by this direction and a shear component in the direction of the face. We notice that this component, sigma sub x cosine phi, as this face goes from an angle of 0 degrees up to 90 degrees, the value of S goes from sigma sub x cosine 0, which is just sigma sub x in this direction, to a value in the normal direction, which would be equal to 0. And because there is no external force in the y direction, that component is indeed 0. The normal stress, that is this stress, it will be S cosine phi, but we just found earlier that S is equal to sigma sub x cosine phi, so this component, sigma sub n, is sigma sub x cosine squared phi. And likewise, the shear stress tau will be S sine phi, that is this term sine phi, and its value will be sigma sub x cosine phi sine phi, and using the double angle formula, that becomes sigma sub x over 2 sine 2 phi. Now this 2 phi is going to be important later on when we look at Mohr's circle. If we evaluate the shear stress as we vary the angle from 0, that is axially, up to 90 degrees, we find that there is a maximum value for the shear stress, and it occurs at an angle of pi over 4. That is, where phi is pi over 4, the sine of pi over 2 is equal to 1, and therefore our maximum value is 45 degrees to the maximum value of the axial stress. Now, if we look at an element that we've removed from this prismatic bar, we can show that this element, when we look at normal stresses and shear stresses, will be exposed to two different mechanical effects: extension in this direction and sliding or shearing in this direction. And both of those components will be important when we consider the failure of different types of materials. Now, a convenient way to represent the relationship between the normal stress and the shear stress at an arbitrary angle in a material is via something called Mohr's circle. And what we're going to talk about here is the origin of Mohr's circle and what we can interpret from it. First of all, if we plot on the abscissa the normal stress, and if we plot on the ordinate the shear stress at some arbitrary point in a material, that will be some point on this plane. If we consider the equations that we've just derived for the normal stress and shear stress, we're going to find that as we vary that angle phi, the locus of the normal stress and the shear stress will trace out a semicircle here. And it will go from 0 degrees to 2 phi, which would be 180 degrees. As we rotate fully to 180 degrees, we trace out a complete circle. Also, this circle indicates where the principal stress is, the principal normal stress, sigma sub x in this case, and the principal shear stress, which remember is half of the principal normal stress. Again, both of those are important to know in terms of failures of material. To prove that this in fact is the equation of a circle, remember the equation of a circle that has been offset by its radius from the ordinate in the abscissa is x minus a squared plus y squared equals the radius squared. And if we substitute for x the normal stress, and if we substitute for y the shear stress, we can use those relationships that we had earlier to prove an identity indicating that indeed the locus of the points of sigma sub n and tau is a circle on the shear normal stress plane.